Lesson 1. Understanding Process Performance and Lean Metrics. In this lesson, we focus on clarifying the meaning of the performance measures we used during our process improvement. We take time to understand the basic concepts and definitions in order to help us better respond on how we can drive the changes. Topics under Lesson 1 would cover understanding the concepts of measurement and how it relates to improvement. We'll talk about linking process performance with the basic lean metrics. We'll discuss concepts on cycle time, yield, and OEE, and how all of this can help guide you and your team in finding out the areas where your improvements will matter more. It has been mentioned many times that unless you measure the improvement, then you don't really improve. We talked about knowing how best we can justify the improvements that they are worth it. Let's look at the lean thinking framework that we are using throughout this program. We started with course 1, where the focus was more on understand the improvement mindset and how we see the waste and how you see the whole, which is the end-to-end process. In this course, we started to understand now how can we make this process flow and move forward. Later, we talk about the importance of standardizing any improvement we make and that we continue to drive improvements as part of our discipline. All of this drives towards improving our process performance in the context of quality, time, and eventually in terms of our bottom line. Let us recall our definition of improvement. When we talk about improvement, we think about in terms of raising the standards of performance. It is not a reactive, but rather a proactive response to doing something better and better. When we talk about problems and opportunities, oftentimes improvements are often focused on addressing problems, and therefore it tends to focus on the gap. For our effort, we want to be able to focus on what can we do to be able to improve our performance into a better level. In order to do that, we need to think about what can we do things differently so that our performance will be better in the long run. The famous Henry Mintzberg mentioned, performance control systems can serve two purposes: to measure and to motivate. When we talk about measuring the performance of our improvement, we put it in the context of how it can motivate us to drive ourselves to pursue the improvement. Before starting your improvement cycle, it is important for you and your team to consider the right measure. To find out what the right measure is, it's important for us to ask questions like, what outcome are we after? What results are you after when you drive your improvement? It might require you to look at other measures and how you can actually influence them. Take note that good metrics or good measures are ones that truly measure the growth of the business. Here are some examples of traditional performance measures. Such examples are machine utilization, efficiency, productivity, overhead use, quality. These are not so unusual measures. Unfortunately, these measures can drive the wrong behavior. Oftentimes, when people are so focused on the measure that they end up pursuing the opposite effect of their improvement, it often results to either an excess buildup or lower quality or even an overemphasis of just purely reducing cost. Therefore, we need to be mindful when we look at our measures that it does not condition us to think about improvement in a negative way. Too often, when we look at our metrics, there is too much focus on meeting the number and not the intent and the outcome. We call this behavior counterintuitive, and almost all of us have been guilty at one point in time. We look at utilization, output, on time, and anything related to standard cost as something we would like to maximize. And yet, repercussions are often not seen or even ignored. When we now look at our metrics or our performance measures, we need to make it simple, make sure that we can easily gather data. Keep in mind that performance measures are oftentimes a signal that things are working or not working. The goal is not to be overwhelmed with too many measures. Otherwise, they become more of a report rather than actually a way for us to be motivated in making our process better. Ultimately, our goal is to be able to influence our business performance, be it in the form of a bottom line or a top line. We want to make sure that our efforts drive these performances. Looking at this hierarchy of performance measures, we can deduce that a big chunk of the effort we do is to drive performance and how performance can affect cost. Some examples or common examples of performance measures that we will talk about in the succeeding lessons will be OEE, cycle time, first pass yield, throughput, and lead time. These are common lean measures that are often mentioned and often used. It's important for us to understand what they mean and what they can represent so that they can better be used when we drive our improvements. One of the more popular and important metrics in lean is all about measuring time performance. This can be in the form of a process time, lead time, and cycle time. Many times people get confused about what these measures are, so it's important for us to have a better understanding of what they truly mean. One of the basic measures in lean is process time. Process time is simply the time that is needed to make your product or service. Oftentimes, process time is associated to an activity or a task or a procedure that is truly necessary to create the output or the results that you wanted. However, process time might be value-adding or could have a non-value-added activity but necessary for the business. And sometimes you can also have some non-value-added activities embedded to it. But in general, process times are simply those that are truly important for performing the task at hand. Such examples would be like the filling part or the baking are examples of process times where we often see in our own areas. Another important and common measures in lean is lead time, also known as flow time. Lead time refers to the total time it takes to complete the work from beginning to end. This encompasses most often other activities or other processes beyond a single activity or task. It usually captures the process where everything begins until ultimately the product is in the hands of the customer or where it matters more. We need to make sure we define what and when we start and when it is truly finished. When comparing lead time and process time, we can see that lead time encompasses more than a few process times. Another thing about lead time is that it also captures more than the actual activity, but also those times that work may not be happening and therefore non-value activities or items happen. Lead time is oftentimes viewed as the metric that customers often feel. They would often ask, how long will it get to me? And lead time is that one metric that determines how it is going to be for our end customer. A third and most important lean metric is called cycle time. Cycle time refers to the time it takes to produce one unit or item from beginning to end. It is the time it takes for you to start the work again on another item. Oftentimes, when we talk about cycle time, some people often associate cycle time to process time. They can be the same provided you're only working one piece at a time or one item. However, many of our processes do not process one item at a time. Sometimes you have many people working on many of these items at the same time. We now refer to this process as batch production. When you are now involved in a batch production, you cannot measure one item at a time because most of the time you use a machine that handles or produces more than one output. So it is impractical for us to observe the time between the two successive outputs. So therefore, when we now measure cycle time in a batch production, we can now estimate it by using the simple formula here. Cycle time is simply equal to how much time you had divided by the total number of units produced. By understanding this concept of cycle time, we are estimating how often will the next item come out of the process. That is now how we interpret cycle time. Assuming that you're only working on one item at a time, we can compare lead time, cycle time, and process time using the diagram here. Lead time refers to the total time it takes to truly complete the work, while process time oftentimes is referred to the value-added portion of the work, and cycle time includes some other activities that may not necessarily be value-adding. Let us have an example. Let's say that for a given burger patty production line, you are able to produce 100 patties in 1 hour. What would be the average cycle time per patty? Using the formula of a process where we are able to produce many in a given time, we can simply compute for the cycle time by getting the total number of minutes in 1 hour, which is 60, converting it to seconds, divide by the total number of patties, which is 100, gives us 36 seconds per patty. This means that if I were to stand at the end of the line of this burger patty line, every 36 seconds, a patty would come out. Another illustration is looking at an oven where you have a capacity to bake 60 loaves of bread for 45 minutes. The loaves are taken out from the oven, cooled down, and removed from their baking pan, and eventually transferred for a total of 100 minutes. What would be the lead time to complete the production of the 60 loaves? Second, what is the cycle time to produce a loaf of bread? To answer the first question, we simply account for all the processes and their times and add them up to be able to capture our lead time. Hence, we have 45 minutes of baking, 100 minutes of cooling, removing from pan, and transporting gives us a total of 145 minutes for the 60 loaves of bread. The cycle time is 145 minutes divided by the 60 loaves of bread, which is the time it takes to produce the 60, which gives you a total of 145 seconds per loaf of bread. So in essence, if I were to stand at the end of the line, when I looked at the loaves that have been cooled down, we can estimate that every 145 seconds, a loaf will be done. When we now use these lean metrics on time, what we wanted to happen is to make things flow. We want to make things flow because by doing it this way, we know that the lead time can be reduced. For batch mode of work, normally, this increases waiting time and work in process. Because when you move by batch, you tend to accumulate what we call work in process, thereby resulting to longer lead time and greater cycle time. By moving to a one-piece flow, we promote less work in process, less waiting time, resulting to lower lead time and lower cycle time. The second kind of metric that we wanted to talk about is that metric that measures quality performance. Under this metric, we talk about first pass yield and rolled throughput yield. Normally, when we talk about measuring quality, we always refer to looking at what would be the standards by which these products or services becomes acceptable to our customers. In order for these products to be acceptable, we always refer to some form of standard or characteristics that makes the product desirable. Some basic concept in quality before we talk about the quality metrics. In quality metrics, it's important to distinguish between what we refer to as a defect, a rework, or a reject. A defect refers to a characteristic that an item has that it doesn't meet the standard. A rework is where you have to correct the defect to make the product acceptable, while a reject and scrap is where the defect lends the product by itself unacceptable and therefore oftentimes disposed. A basic measure of quality is yield. Yield, in its simplest form, measures the proportion of good items over the total items you have. It is the ratio in which you get to have good items out of what you have inputted into your process. In the examples below, you could see that we have a process where 352 units went into it and only 347 units turned out to be good. This gives us a yield of 0.98 or 98.6%. Another illustration would be looking at the box of donuts on our right, where we can see that there are 11 out of 12 donuts in the box. This gives us a yield of 91.7%. Unfortunately, the reality in most processes are not as simple as that. When we look at processes, it is not often the case that you get to see good items coming out from the process. Oftentimes, if we look at the process on the left, we assume that the scrap is removed and thus you only have 347 units out of the 352. Unfortunately, when you look closely into the process, there can be a hidden process such as inspection, where what we do is we actually screen out the output of the process. And that in the process of inspecting, certain rework is done and the work is redirected or the item is redirected back into the process and becomes a good item. Thus, it might appear that you are producing good items a lot, but a lot of rework was actually done. So one way of measuring yield, a stricter way of measuring yield, is to not include the scrap and not include the rework. As a result, your yield will now be lower. From what used to be 0.98 on the left, it is now 0.7 on the right, because we did not recognize rework as an output. This concept of yield is called first pass yield. First pass yield is where you only measure the good items that you made the first time. No rework or repair or scrap or rejects. You only consider those that were good the first time around. This is called first pass yield. Sometimes it's also called first time yield or throughput yield. When yield is computed after the defects are reworked, it is referred to as a final yield, where you get the final output of the process. It's important for us to distinguish the kind of yield we have. Are we measuring the final yield or are we measuring first pass yield? Eventually, we now apply the concept of yield into our overall process. When we now get the overall yield, we now refer to this as rolled throughput yield. This kind of yield represents the overall yield of your end-to-end process. It is composed of yields from various processes that accumulate to the very end. Simply put it, if I started with 100 items at the very beginning and then I end up with 44 good items the first time around with no rework, then my rolled throughput yield is 44 out of the 100. This is the yield of the overall process. a way for us to be able to compute or establish our rolled throughput yield, we can apply the following approach. First, you have to go back to your value stream map and understand what these major processes are. For each of these process steps, you now compute for your first pass yield. Each process can easily be established by using the input and output of that particular step. Once you have the different yield of each process, you can multiply this yield to give you what we call the rolled throughput yield. Remember, when we try to drive our overall yield, it's important for us to understand the yield of each of these processes, because the process that has the least yield is oftentimes the focus of your improvement. Because no matter how much you make the other process better, it is going to just be eaten up when it reaches a process that has low yield. Some reminders when we apply the concept of yield. Remember that yield oftentimes ignores or does not account for rework and scrap. Therefore, we need to be mindful on how you truly measure your yield. Second, within your product, there could be different defects, and therefore, knowing the defects is not going to be easy when you just look at your yield. When you compute for your overall yield, it's important to match how you compute for it and what the number is versus to what actually came out of it. This will give you a good sense of true performance by comparing the computation you had versus the actual numbers that were produced. If there is a discrepancy between the actual yield versus the computed yield, you might want to ask yourselves what is going on. Finally, when you now apply yield, it's important to consider using first pass yield. First pass yield gives you a better picture of the real quality of your process and helps guide you in where you should improve or focus your improvement effort. By using these two concepts of measures, time and quality, we can now use these ideas to measure our overall performance. One common way to measure overall performance is the use of what we call OEE. OEE, or Overall Equipment Effectiveness, is a common measure of manufacturing productivity. It helps you identify the truly productive resources or time of your process and how you make use of it. If you end up with an OEE score of 100%, it means that you are not only maximizing your time, but you're making good parts as fast as possible with no wastage of time. Truly world-class performance for any process. To measure OEE, we simply take into consideration three components. The first component is to establish the available time that you have for your processes. Second, you establish the performance rate. And third, you establish the quality rate. By getting the performance ratio of these three components and multiply them, we can end up establishing our overall performance. To measure availability, we need to take into consideration the time we use in our production. Oftentimes, we refer to this time as our runtime, and we remove all what we call as the planned stops, meaning time that we don't use for a specific reason. By getting the difference between the planned time and the stop time, we get what we call as our runtime, divided by the total planned time. This gives us a ratio of how well we use the total time that we have. The second component is about performance. To be able to measure performance, we look at how much are we able to produce given the time we have. To do this, we make use of the concept of cycle time, where we establish now how much can we make. Oftentimes, the output of our process is affected by stops. When there are stops, we produce less. Therefore, by computing for how much we should be able to produce compared to the actual production output, we should be able to establish our performance time. The third component of our OEE is quality, which is what we referred as yield. In this case, we compute for the yield of our process. Keep in mind that we should be particular about how we would measure this yield. We often remove the scraps, but we also would like to make sure that we don't bloat our quality by doing a lot of rework. Quality in this case oftentimes refers to first pass yield. To better understand how we can arrive at an OEE, let us take the case of an example of this chicken processing line. For this particular chicken processing line, we have an 8-hour shift that we use, and of that 8-hour shift, only 7.5 is actually used for actual production. The half hour is used for breaks and other planned stops. The actual production time is 6.25. Therefore, the availability of the line is 6.25 divided by 7.5, giving you a ratio of 0.83. The second component of your OEE is what we call performance or efficiency. This refers to the output that happened during that period. If the line is able to produce 100 kilos per shift and we were only able to process 99, then that means the efficiency is 99 over 100, meaning only 99 kilos was used of the 100 that we could have done. And finally, for quality, we now measure how much good items were produced out of the 99. Oftentimes, when we talk about quality, we refer to this as the quality without any rework. For this example, 5 kilos of the 99 was rejected, and therefore the yield or the quality component of our OEE is 94 over 99. If you multiply all of this ratio, you can now get a value of 0.78 or 78.3%. Therefore, our OEE is 78%. How might we now interpret this OEE? Looking at this illustration, globally or world-class wise, we would look at OEE having the following performance rating. A 100 is a perfect performance. The 85% is world-class. 60% is quite common for many manufacturing processes, and 40% is quite low. If your OEE is low, that means you are incurring a lot of waste. From the view of an improvement mindset, we need to identify what is causing or what is made up of those low percentages and how can we convert them into better performances. So by comparing your OEE with this standard of performance, we can now use this to help us focus on your improvement efforts. What part of your process would you want to focus on in order to drive better performances? And even if you are meeting your OEE and you're at 80%, how can you make your OEE better? So it's not about reaching an OEE that's as a goal, but rather seeking to make your OEE better and better every time. Once we have a good understanding of our OEE, we can now make use of this as a way to help guide our improvement cycles. When we now jump into finding ways to make our process better, OEE is a good reference for us to dissect how well we use your time and the quality that comes out of your processes. When using OEE, we can now go back and understand where those losses are. By focusing on these losses, this will give you a clue of where you can focus your improvement cycles and how you might want to bring in the right resources and investigation for your team. You can look at all of those green areas that constitute losses and therefore opportunities to make your performance better. We also realize that your OEE cannot be a one single number. We all know that OEE can change at different times due to many circumstances. So one way for you to be able to understand your OEE is how can your OEE be more consistent? This is where we now try to see variabilities in your OEE. If your OEE fluctuates between 60 to 80%, then that's another cause of observation you might want to look into. These variabilities are good inputs to your improvement effort. By looking at this OEE measure that you have, Armand Feigenbaum has actually mentioned back in the 1970s that many times when we look at our processes, be it manufacturing or even in our offices, we have what we call many hidden factories. Hidden factories are the things that happened that oftentimes are ignored or not seen, and therefore creates the impression of performance. Without recognizing this hidden factory, we end up not explaining why such performance is happening. These performances that are attributed to hidden factories can be as much as 20 to 40% of your capacity which is lost. This can be oftentimes be undocumented and therefore not seen or not paid attention to. And they often result to a decrease in quality or an inefficiency in your operation. Some examples of these hidden factories would be having multiple versions of specs, or operators reworking their parts at the workstation without anyone knowing it, or line supervisors speeding up the cycle to catch up when they're behind, not realizing that certain steps are missed. Sorting mix-up can also happen. There is a lag in the reporting and therefore people don't know something until it's worse. Or making it difficult for people to share ideas of improvement because of red tape or bureaucracy. Or finally, operators are not carrying out the right maintenance or preventive maintenance on the machine, and oftentimes the parts are damaged and yet unnoticed, therefore causing a massive failure in the future. How about you? What hidden factories have you seen or have existed in your own experience? In general, when we now identify these hidden factories, we can look at 4 areas that is often captured in your OEE. This could be in terms of losses in our schedule, losses in terms of the availability that we have, loss in performance, or loss in quality. By looking at these losses, you would notice that we will experience some areas in your processes that most likely will contribute to a lower availability, lower performance, or lower quality. For example, if you talk about lower availability, that means that you might have very long setup time. And that means that could be one area by which you can drive your improvement effort. Or performance loss, where the time it takes to produce an item is quite long, and therefore you might want to drive your lean efforts into making your cycle times smaller. Or you can focus on the quality, where you want to make sure that you don't make mistakes, and you apply concepts like mistake proofing or visual management to avoid all of these unnecessary losses. 3 important messages I'd like you to remember out of lesson 1. First, it's important to focus on knowing and understanding the key measure that your improvement effort should focus on. Second, it's important to improve on cycle time, which will help improve our lead time. When we improve the speed by which we produce our output, the overall lead time will also be reduced. Third, it's important to understand the context of quality and how quality is measured in terms of your yield. Measuring yield is important because you want to make sure that you have a real grasp of what is the true quality of your process.